Okay, welcome back to chemistry. So I want to get into a little bit about acids. Today we're going to look at acid dissociation reactions, and I want you to be able to identify what are my conjugate acid-base pairs. So really important, so as we get into doing more with acids, and if you do more with acids in the future, like into buffers, it's really important to be able to identify where the hydrogen's moving and how that sort of pair that's moving to is connected to where it came from. So let's look at a little example. So first one, I'm going to take hydrochloric acid. Hydrochloric acid, I'm going to combine that with water. So we're looking at acid dissociation, so I'm always going to be having an acid dissolved in water. And what's going to happen, always ends up happening, is I'm taking one hydrogen and I'm moving the hydrogen off my acid onto something else. Now remember our definition that we're using now. So an acid is something that donates a hydrogen, and base is something that accepts a hydrogen. So in this case, water is my base, is accepting the hydrogen. What am I going to be left with? Well, my hydrogen ion itself is not taking any electrons, right? So I'm going to be left with chlorine, which now has retained that electron that came from the original hydrogen, so it has a negative ion. And now I'm going to have on the other side this hydronium ion, which now has a positive charge. So this has gained that one proton, but it didn't gain any. My water gained one proton, but it didn't gain any electrons, so now it has an overall positive charge. Importantly, notice that this is a one-way arrow. So this is not described as an equilibrium, that this is a strong acid. My strong acid entirely dissociates. So all of the hydrogens will come off of my chlorine ion, and I'll be left with a bunch of hydronium floating around and some chlorine. So the hydronium, this hydrogen is very reactive. My hydronium is very reactive. So this is sort of an unstable molecule. So this is what makes acids particularly dangerous or useful, depending upon your point of view. And this is a strong acid. So you just need to know the 6 strong acids that I've listed before. So you need to know the nitric acid, sulfuric acid, hydrochloric acid, and then the acids that are from the halogens. So hydrochloric acid, hydrobromic acid, and hydroiodic acid, those are all strong acids. If you know those, then everything else is going to be weak. So for the strong acids, we're going to draw a one-way arrow. This is what's going to happen. So let's think about how we're going to name these, right? So we're going to have, this is my acid. It gives up the hydrogen. And this is my base. It's accepting the hydrogen. Strong acid. Okay, let's go to a weak acid. So weak acids are vastly more interesting. So let's see what those look like. So here I'm going to look at this one. So how do I know this is acid? Well, it starts with a hydrogen. Also, I just need to get used to this one. So this one's going to show up a lot. This is acetic acid, also known as vinegar. Same idea, though. So I'm going to take my hydrogen, and I'm going to move it off my acid and onto the other thing. That other thing must be a base. In this case, water is acting as my base. Again, this is my acid dissociation. So what am I going to be left with? Well, now I'm going to have this thing. I'm going to have my acetate polyatomic ion. And it's keeping that electron that hydrogen had is just the naked proton my hydrogen is moving. So I'm going to be left with that extra electron there. And now I'm going to have an extra proton on my hydronium, and I'm going to be left with something that looks like this. So I'm going to have H3O plus, my hydronium ion. Notice the double arrow there. So this is really important. So this tells me that not only is a forward reaction happening, but also the reverse reaction is happening. So this is not a strong acid. It's not one of the 6. So this is not a strong acid, which means that if I look in solution, I will find all of these things floating around, right? I will find some of this acid next to the hydrogen. I'll find some of this floating around, and I'll find some of my hydronium and a whole bunch of water floating around because it's a solution, right? So let's name some things. So in this, I have my base, my acid, which is donated the hydrogen. I have my base, which is accepting the hydrogen. Right? So the key thing, though, is that with a reverse reaction, that I also have an acid reaction going in the opposite direction, right? So now my hydronium ion could, in the reverse direction, give up a hydrogen, which would join in with my acetate polyatomic ion and would reform this acid complex. So we can write the reverse direction if we want. So we can write this as H3O plus this thing, H3O2, right? All I'm doing is I'm just changing this, flipping this. It makes no difference that chemically it's the same thing. And now I have HC2H3O2, and I've regenerated my original water. So notice the hydrogen's moving, and I'm going to have, this is now my acid, and this is now my base. So I have 2 acid-base reactions that are happening here. So one acid-base reaction in the forward direction, and one acid-base reaction is happening in the reverse direction. So we're going to combine these together and just have one reaction that we write, and we're just going to use the word conjugate to mean it's going in the reverse direction as I've written it. So in this case, right, My hydronium ion is acting as an acid. So on this side, I'm going to say, well, this is the conjugate acid. This is going in the reverse direction. This thing is accepting the hydrogen going in the reverse direction. This is my base going in the reverse direction. So I'm going to call this my conjugate base. Okay. So now I have a name for everything here. So I have my forward direction, I have my acid, my base. In my reverse direction, I have my conjugate acid and my conjugate base. And the definition is still the same. So my acid is donating a hydrogen, and my base is accepting the hydrogen. Conjugate just means it's going in the opposite direction. Okay. What I'm going to ask you to do is pick out pairs, right? So there are connections between these. So notice that my acetic acid and my acetate polyatomic ion, right? They're related to each other. They differ by just one hydrogen. My water and my hydronium ion, notice they're related to each other. They differ by one hydrogen. So these pairs, one on the reactant side, one on the product side, that only ever differ by one hydrogen, those are going to be my conjugate acid-base pairs. So this is really helpful. So I know my acetic acid is going to become this acetate polyatomic ion. I know my water is going to become hydronium ion. It doesn't matter which way. Right? I get the same pairs if I've written it in the opposite direction as well. So I'm going to be able to do this. Let's try another one. So let's take something amphoteric. Why not? So amphoteric means it could either function as an acid or a base. So usually these are polyatomic ions that have charges of more than one and allows more than one hydrogen to be associated with. But let's so I'm going to take this one. So this is my carbonate polyatomic ion with one hydrogen, right? Not two, just one. So it has the CO3. The carbonate has a charge of 2-. I put one hydrogen on this. So I'm going to combine this with water, and I'm going to have this function as an acid. Let me think about that, right? So I'm going to tell you this is not one of the strong acids. So if there's going to be an equilibrium, I'm going to draw 2 arrows. I'm going to take my hydrogen. If this is functioning as an acid, this must be my base. I'm going to move one hydrogen. That's all I'm ever doing. I'm only ever moving just one hydrogen. Don't move 2. I'm going to move one hydrogen. I'm going to be left with CO3. Now it's kept all those electrons and has lost one proton. So now it has a charge of 2-. And I'm going to have H3O plus. I have my hydronium ion. So going in the reverse direction, let me think about this. So going in the reverse direction, I have an acid and base, or we'll call them, since they go in reverse, conjugate acid, conjugate base. So here I have H3O. I'm moving a hydrogen from here to here. The thing that's given up the hydrogen, I'll call this my conjugate acid. And the thing that's given, or that's accepting the hydrogen, I'm going to call that my conjugate base. So I'm going to make some pairs. So my acid on one side to the base on the other. So notice that this acid and this conjugate base differ by one hydrogen. Acid and base from one side to the other. So this water and hydronium ion differ only by one hydrogen. So a key thing for they only differ by one hydrogen. Okay, so that's how to identify these conjugate acid-base pairs. They're a handy thing because notice in my strong acid, my strong acid, here's hydrochloric acid again. So I have my chlorine that's generated. My strong acid, right? So this is my my acid, this is my base, this is my, if this had a reverse direction, which it doesn't, this would be my conjugate acid, this would be my conjugate base. So notice my strong acid, right, means this hydrochloric acid is really good at giving up hydrogens, right? And this is true on this side then. So this base is really bad at accepting hydrogens. So one of the things we'll say that strong acids have weak conjugate bases, right? So the conjugate bases are not very good at attracting hydrogens. And conversely, we can say, well, this is something that's equilibrium. It's a weak acid, so it's a weak acid. So this conjugate base, it's pretty good at attracting a hydrogen. So they go hand in hand. So if I have a strong acid, I must have a weak conjugate base. And if I have a strong conjugate base, that means it's a weak acid. So one way we'll be trying to think about these is the strength of things. So there's interesting things we can do. So I mentioned this is amphoteric. So we can flip it around and we can write the opposite reaction, right? So if I do this opposite reaction, sorry, that's not what I want to do. I want to do, this is amphoteric, so I want to be able to write this not only as an acid, but I also can write this as a base. So let me think about this. I'm going to start with the same stuff, right? So I'm just in water, so I have HCO3 minus, and I'll combine that with water, but instead of acting as an acid, this can act as a base. Right? If this is my base, then this must be my acid. Okay? So that means the hydrogen is going to come from my water and go onto the carbonic hydrogen carbonate or that thing. So what am I going to be left with? I'm going to be left with H2CO3. It is carbonic acid, so soda pop, right? And then I'm also going to be left with, now I've lost a hydrogen here, so what do I have? I have a hydroxide ion, right? So going in the reverse direction, right? So now this would be my acid because it would donate the hydrogen, and this would be my base. So this is going to be my conjugate acid and my conjugate base in the reverse direction. So notice what happens. So when this functions as a base, I generate a hydroxide, and you really need to recognize hydroxides as base. So one way or another, we often get to hydroxides as bases. Not all the time, but is a pretty good indication. So this is amphoteric, can function as either an acid or a base. Water is also amphoteric. It's entertaining to write that one out. You should give that a try. And the reaction starts like this. See if you can do that one. So water is amphoteric. You're going to move a hydrogen, see what you get left with. Anyway, I hope this has been helpful, and we'll see you in class. Bye.